Let's start the next section on Cauchy sequences and complete metric spaces. In this section, we are going to extend the theory of sequences of real numbers to sequences in a general metric space. So, we start the section with this definition of a subsequence in a metric space. Definition 12.4.1. Let Xn be a sequence in a general metric space X, D. We have already talked about why we use superscript here when talking about sequences in a metric space. We generally do not use subscript to denote the sequence terms. The reason is that sometimes our metric space itself may have sequences as points in it. So then if you use subscript, you have to use double suffix to write the terms of those sequences which are terms of a sequence. To avoid this, we use superscript. But if you still want, you can use subscript. The author has used superscript. And to further avoid confusion between this superscript and exponent, we enclose it within brackets. And you also already know that here m is some integer. M may be 0, it may be 1, it may be actually anything. It may even be 1000 or minus 1 million, anything it can be. Okay, so this is any sequence in this metric space X, D. And then what we consider a sequence of integers. Okay, these are ordinary integers, n1, n2, n3 and so on, such that they are all at least m. That means this starting index of our original sequence, and this sequence of integers is strictly increasing in this sense that as you go down the sequence, you get larger and larger integers. Then we call this sequence xnj, where j varies from 1 to infinity, a subsequence of the original sequence. That means from the original sequence, we only keep those terms where the superscripts are these integers. Okay, depending on what this sequence of integers is, we will have this subsequence. And if you go back and see the definition of a subsequence of a sequence of real numbers and match that definition with this one, you will see that essentially this is just that definition. The only difference is that now we have a general metric space and there we had the metric space of real numbers with the usual metric. That is the only difference. Next we have examples 14.4.2. Look at this sequence. The parenthesis may be a bit confusing at first, but you forget the outer parenthesis for a moment and consider the inner parenthesis. Inside of them, what do you have? 1 divided by j square, 1 divided by j square, where j varies from 1 to infinity. J is a positive integer. So that means this is a point in the plane where the x coordinate is 1 over j square and y coordinate is also 1 over j square. As j varies over the set of all positive integers, you get the terms of this sequence. All the terms are points in two-dimensional plane R2. So that is why this is a sequence in R2 and this is a subsequence of this other sequence where the points are 1 over n, 1 over n. Here also n varies from 1 to infinity. In this case, the author has also written that nj is j square. You need to first of all make sure that this j square itself is an increasing sequence of integers. As j increases, do we have the terms increasing in a strict manner? Yes. 1 square is strictly less than 2 square. 2 square is strictly less than 3 square, that way. So that is why by the above definition, this is a legitimate subsequence of this. What is the first term of this sequence? 1, 1. The second term is 1 divided by 2, 1 divided by 2. The third term is 1 over 3, 1 over 3. Whereas, what is the first term here? Same as this one, 1, 1. but the second term is 1 over 4 comma 1 over 4. So we are only choosing some terms from this sequence to form this other sequence, which is a subsequence. In a similar manner, this constant sequence of real numbers, this time all of whose terms are equal to 1, is a subsequence of this other alternating sequence where the terms alternate between 1 and 0. I want to say a bit more about this second situation. Now this is how you can see this present situation. I have used the third row here in this table to write the terms of the sequence. This is the sequence and this is the subsequence. We are coming to the subsequence afterwards. So these are the terms of the sequence. They extend in this direction without any end. So you are looking only at a finite portion of this entire thing. And I have used the first row to index these terms using positive integers. It's not necessary you have to use positive integers, but why not? Because they are convenient. So this means that this is the first term, this 0 is the second term, this one is the third term, like that. And then we think of the subsequence. The subsequence consists of those terms in the original sequence which are equal to 1. That means these terms, because the subsequences are to also be indexed by what? By the nj's. So those nj's, according to our definition of subsequence, have to form an increasing sequence of integers themselves. And obviously this should be the nj's, because we only want the ones, the terms which are equal to 1 from the original sequence. So this should be n1. This is not n1, this one is n1. n1 is equal to 1, n2 is equal to 3, n3 is 5, n4 is 7, and so on. That means the nj's form the sequence of positive odd integers. Is that an increasing sequence? Yes. 1, 3, 5, 7, all the terms are strictly increasing as you go down the sequence. So that is why this is a legitimate subsequence of this sequence. And next we have lemma 12.4.3. Let x then be a sequence in any metric space x comma d which converges to a point x naught of the space. Then any subsequence of this sequence also converges to x naught. And you can clearly see that this is the general version of a previous result that we saw and proved for sequences of real numbers. And for the proof, the author asks us to see the first exercise at the end of this section. So when we solve the exercises, there itself we will prove it. Actually the proof is nothing unfamiliar to you. It's that same proof for that result that we saw for sequences of real numbers, which is the special case of this. For such sequences, you just have to modify that proof in the language of metric spaces. That's it. So by the above result, every subsequence of a convergent sequence is convergent, and in fact it converges to the same limit as the original sequence. But the converse of this is not true. For example, you consider this alternating sequence which is divergent. Why is it divergent? Because it's not even a Cauchy sequence. You try to see why that is the case. But in spite of being divergent, it has this convergent subsequence, and there is another one consisting of only the zeros. So for a convergent sequence, all subsequences are convergent. But if in a sequence you have a convergent subsequence, then that does not say that the sequence has to be convergent. This is a counter example to this converse. But in spite of that, how can we say something about this situation? Say the sequence itself may not be convergent, but it has a subsequence which is convergent. Is there a way of knowing that a sequence will have this property? So the next definition and the subsequent result is about that. And that next thing is the definition of limit points, but limit points of sequences. Let x then as usual be a sequence in a metric space x comma d. and let L be a point in the space X. Then we say that this L is a limit point of the sequence if for any positive real number epsilon and any integer capital N which is at least as large as the starting index m, there exists some integer small n greater than or equal to that capital N such that the distance between x n corresponding to this integer n, you have a term of the sequence xn, the distance between that term and that point L is at most epsilon, is less than or equal to epsilon. If this happens, then we say that L is a limit point of this sequence. What is this definition saying? I mean, how can we make sense of it? What lies behind these technical things? The idea here is this: you have a sequence in a metric space. How do you imagine a sequence? You have a metric space, and a sequence is a collection of points where there is an order to how the points appear. There is a first term, then there is a second term, a third term, and so on. It goes without any end. All right. And L is also some point in the space. Okay. So what these conditions are saying is that no matter how small your epsilon is, how small your epsilon is means what? This type of statement that distance is less than or equal to epsilon means that you are essentially considering some region around the point L of size epsilon. By that, what I really mean is this: you consider the closed ball centered at L having radius epsilon. I think I better draw a diagram for this thing. That way it will be easier to understand. So we can understand these conditions with this diagram. In this diagram you see a few things. You see the first 5 points of this sequence. Points means terms, which are points in the metric space: x1, x2, x3, x4 and x5. Of course there are others wherever they are. I have drawn this in a kind of general manner so that x3 and x5 lie inside this circular region, but the other 3 lie outside. Anything can happen in general. And you also have to understand that this diagram does not mean that the plane of this whiteboard is the metric space. This is only a schematic diagram. It tells you how you can think of these things using diagrams to just understand the scheme, what the entire setup is. It's like Venn diagrams. Okay. And what is this circular region? This circular region is the closed ball I was talking about just now, which has L as its center and epsilon as its radius. It is by definition the set of those points in the metric space whose distances from that point L are all less than or equal to epsilon. So they lie either at the boundary or inside. Now what are these conditions saying? These conditions have 2 things for you to choose: epsilon and capital N. These are your choices. They are arbitrary. The only thing you have to make sure is that you have to choose them in such a way that these restrictions are intact. Epsilon can be any real number but positive. Epsilon can be large, it can be 100 million or even a billion, or it can be extremely small, 1 divided by 100 million or 1 divided by a trillion. Anything you can choose. The only thing is that it needs to be a positive real number. So corresponding to any such epsilon, you have a closed ball centered at L. That is the first choice. The second arbitrary choice is this capital N. What is this signifying actually? The significance of this capital N is that you are putting further restrictions on the sequence. In what sense? In the sense that you are to consider only the terms of the sequence that start from capital N, not from small n, not all the terms. Say you choose this capital N to be 100, okay, then with this epsilon and capital N equal to 100, the condition says that then there exists an integer greater than or equal to 100 such that the term of the sequence corresponding to that integer is close to L in this sense, that that term lies within this region. So there are two things. First, you can choose epsilon to be very small, making this ball really very small. And the second thing is that you can also put further pressure on this entire thing by choosing this capital N in whatever way you want. You can choose this capital N to be 100 or 1000 or 1 lakh, 1 million, anything. There has to be an integer which is at least as large as your choice of n, so that the corresponding term in the sequence lies inside this ball. Essentially, this just means that if you have chosen an epsilon and say you have fixed epsilon, you are not going to change epsilon for now, then you keep on choosing larger and larger n, you should keep on getting more and more terms further and further down the sequence, all of which are lying inside this ball. And if this happens for any such epsilon, then we say that this L is a limit point of this sequence. So do you see the tendency of the terms of the sequence, or the tendency that the sequence should have in order for it to have L as a limit point, that some of its terms should become very close to L, not the entirety of the sequence, but some of them. Okay, so that's the idea. When that happens, then L becomes a limit point of the sequence. And this is how the idea of limit points of sequences is related to subsequences through this proposition 12.4.5. Let Xn as usual be a sequence in a metric space x comma d, and let L be a point in the space. Then the following two conditions are logically equivalent. You see only one here, but I will write the other one also. One of them is this condition that L is a limit point of our sequence. And this is the second condition. There exists a subsequence of our original sequence that converges to that point L. It means that if any one of these two is true, then the other one is also true. In that sense, they are logically equivalent. And for the proof, we have to see the second exercise. It's a bit ironic when someone starts studying this book now. They think that the proofs will be available. Many proofs are available, but even a greater number of proofs are not available. For example, this one. If you see this proposition and you see that you will get some idea for the proof by looking at this exercise, you go there and you will see that the exercise simply asks you to prove this proposition, and that's just it. Sometimes, of course, the author has supplied ample hints for proofs, but most often there is nothing. We are supposed to figure out the proof ourselves. But anyway, we will see the proof when we solve these exercises.